Here are the answers to the assessment on Investigation 1, Atomic Structure. Now, FYI, there are more questions in here than what you saw on your test. So not only will you find the answers to your particular test questions, but you'll also find some extra ones that you can use as practice. So if you know you're interested in doing a retake, there's more questions in here for you to practice. Now also feel free to forward this video to any point that you need, so you don't have to let the whole thing run if you missed question 16. Well, then obviously just fast forward it to the end, and you can jump around and dig for just the questions that you need. The first 4 are examples of questions that ask us to interpret the difference between an element and a compound. Elements should have all atoms the same, only one type of atom, like ozone. It's okay if they're grouped together. It's called a molecule when you've got groups of atoms bonded together. But ozone could also be called an element because the atoms are all the same. Compounds have different elements bonded together, like sulfur and oxygen. Now, we would call all of these molecules because they're all groups of atoms that are bonded together. But elements have to have the same atom. Compounds have different atoms. Now, there are some elements that just exist as individual atoms, and then there are some here like oxygen O3, or here's a couple other examples. Oxygen can also exist as O2. Some elements like to come grouped together. The atoms just end up being more stable when they're grouped together. And that's okay. In a few weeks, we'll kind of learn about why that might be. Some elements are just individual atoms. That's okay too, as long as the atoms are the same. We would call it an element. If there are different atoms bonded together, that's a compound. And again, all of these could be called molecules because they all have 2 or more atoms of any element bonded together. Molecule is a very general term, whereas going element or compound gives us a little bit more detail on what kind of atoms are bonded together. These 4 have you interpreting a model and connecting it to the formula of the compound. So can I use the key and add up the atoms of each individual element and then link that back to the original formula? So all I had to do is just kind of look at the key to see, okay, the black atoms are carbon, how many carbon? The white atoms are hydrogen, how many hydrogen? And then some of them also had oxygen. Those are the red. So how many oxygen atoms? Just count them up and then put that together in the formula. The little subscripted numbers tell you how many atoms of that particular element are in the compound. These usually went pretty well for us on the assessment, but there's some extra practice here if you need it. The next 4 are being able to model a solid, liquid, and a gas. So the solid particles should be packed real tightly. The solids are real rigid because of that tightly packed atomic structure. Liquid particles have a little bit more space between them. There's a little more energy. They can flow and move past one another, like liquid mercury. Or a gas should have the particles spread far apart. The gas particles have the most energy. They're moving all over the place. They totally fill up the container, kind of like this flask of chlorine. It's a yellow toxic gas, and it totally fills up the entire container. Liquid bromine would look like B then, kind of like liquid mercury. Those are the only 2 elements on the periodic table that naturally exist as a liquid, mercury and bromine. These questions went really well. But then sometimes we struggled with the phase change. And I think there's 2 ways to think about the phase change, but the most foolproof way is to think about these models in your head. Think about what it looks like to be a solid, liquid, gas. How are the particles arranged? Are they close together? Do they have low energy, high energy? Are they far apart? Well, now let's see what kind of change we're doing in this picture. So this first picture is iodine vapors. So purple iodine vapors are turning into a solid on the bottom of a cold glass container. Okay, so I'm going from gas to solid. So now let's think about what's happening to the particles. If I look back at these pictures, if I'm going gas down to solid, well, in the solid phase, the particles have a lot less energy. So those gas particles must have lost energy to the surroundings in order to go from gas back down to solid. If I'm losing energy, that's exothermic. I'm releasing energy. I would explain it in terms of the phase of the particles. Well, if I'm going from gas particles that have high energy down to solid particles that have low energy, then the gas particles must have released their energy. Now the opposite is true in the second picture. Here's solid iodine that's being heated. That might be another hint. We're adding heat so that the solid particles are going into the gas phase. So this one's going solid to gas. Well, again, now if I think back to these particle models, solid to gas, oh yeah, the solid particles are gaining energy to go into the gas phase. That's got to be endothermic. Or maybe you notice the word too, it's heated. Endothermic, requiring energy. Yeah, I have to add energy to go from solid to gas. Here's melting. Sulfur melts with just a Bunsen burner. I mean, you could even heat it with a match. Sulfur has a relatively low melting point. But now here I'm going solid to liquid. And so I think about the arrangement and the energy level of the particles. Well, yeah, liquid particles have more energy than solid particles. So I must be adding energy. Endothermic. Or think about what happens when you melt something and you have to add energy. Even though like ice cubes melt without necessarily a Bunsen burner, they're still absorbing energy from the surrounding air. And then the last example is liquid bromine vaporizing. So the liquid bromine is turning into this kind of orangey colored vapor. So I'm going liquid to gas. And then I say, okay, well, what's happening to the particles? Well, yeah, in the gas phase, they have more energy. So this must be endothermic. This would require energy. I have to add energy. So instead of thinking about like, you know, am I heating it? Is it going to feel hot or cold? Think about it in terms of the arrangement and the energy level of the particles. What phase am I starting with? What phase am I going to? Did the particles have to gain energy to get to that new phase? Or do I have to remove energy to get to the new phase? Awesome. Moving on. These were, for the most part, just fine. Each had some kind of an isotope: neodymium, californium, americium, and bohrium. And again, you would have only had one, but now you've got extras that you can use to practice if you got this one wrong. And so the key is that they give me the atomic number. By definition, the atomic number is the number of protons. They do tell me that the atom is neutral. And so neutral would mean that protons and electrons are the same. And then to get the neutrons, I have to subtract. So the mass number, the atomic mass, is a combination of the protons plus the neutral neutrons. The electron mass is so small that we really don't even consider it. And so if I know the protons and I know the atomic mass, which they're giving me, so the mass is this number after the name. This would be the mass. Here's the mass. And here they're always representing the mass of one particular isotope, because we do know that often more than one isotope exists for a particular element. So they're saying, yeah, I want you to use specifically the mass of americium as 241. So I don't really need a periodic table then to look up the mass. They're telling me. They're also telling me the atomic number, which I know then is the number of protons. It is the number of electrons in a neutral particle. And then I just take the mass and subtract the protons, and the remaining mass is the neutrons. Okay, so these are a little bit all over the board. The key is that you have to look on your periodic table to find the weighted average mass of a particular element in order to interpret these isotope graphs. So for example, strontium exists as isotopes with mass 87 and 88. If you look up the mass on the periodic table, you'll see 87.65. Well, maybe here's where I would start. If the two isotopes, 87 and 88, were equally abundant in nature, well, then I would just add the masses and divide by 2. If it was choice B, in the case of strontium, then the weighted mass should be 87.5. If they were equally abundant, we'd add and divide by 2. It should be 87.5. It is not 87.5 on the periodic table, which then just tells me that these isotopes are not equally abundant. When I see that the atomic mass on the periodic table is a little bit higher than 87.5, then I know that the heavier isotope must be a little bit more abundant. The heavier isotope being the mass 88 in orange. Oh. Now check out something like this palladium example. Palladium has isotopes with mass 106 and 107. So if the isotopes were equally abundant, then it would look like graph C, and the periodic table should say 106.5. So now you have to look up this number on the periodic table. Periodic table. And maybe that's where we sometimes got stuck on these. You have to look up the weighted atomic mass as it appears on the periodic table. So for palladium, I see about 106.42. Okay, so they're not equally abundant because 106.5 is not the real mass in the periodic table. And instead, the periodic table's mass is a little bit less. So then I know that the lighter isotope must be a little bit more abundant. The lighter of the two being the mass 106, which is the blue part of the graph. Oh. And then another example would be germanium, having isotopes mass 72 and 73. If they were equally abundant, I would add them up, divide by 2. They are not equally abundant, so I would have to look at the periodic table to find the weighted average mass. If I add them up and divide by 2, I should see 72.5 AMU. But instead it's 72.63. Oh. Okay, so then it's not 50-50, and instead the heavier isotope is more abundant. So it must be germanium 73 for the bigger piece of the pie. Cool. All right, I like those. We had a couple then interpreting the Bohr model of the atom. The key with this one was that we want to know which transition will require the input of the most energy. So if I'm adding energy in, first I need to know that the electron should be transitioning to a higher energy level. So right away, I can tell you that it's not A, it's not D. A and D show electrons falling from a high level down to a low level. That should mean the release of energy. Oh, this one is looking for the greatest input of energy. So the electron should be going from a low level to a high level. B seems to only jump from level 1 to level 3. So that's only 2 energy levels. Same with E. It's showing a jump from level 3 to 5, just a jump of 2 levels. But C is going from level 3 to 6. So an increase in 3 energy levels would require the most energy. Oh, tricky. All right, and then I kind of like this one. So this is being able to put a couple things together. So the first image is a portion of a Bohr model showing electrons all going from a higher level down to a lower level. So they should all be releasing energy as they return down to their particular ground state. Now again, ground state doesn't have to mean energy level 1. Ground state just means where the electron would typically be found. Which spectrum in the second diagram most accurately would show the expected emission spectrum for atoms of this element? And then I explain it. Okay, so look at transition A and C. So they're both just going down 1 energy level. So they should be releasing energy, but since it's only a transition of 1 energy level, we should just be releasing a small amount of energy. It doesn't matter if I'm transitioning from like level 4 to 3 or level 2 to 1. If it's a transition of 1 energy level, it's a low energy transition and I should see a low energy color. So that might correspond to the 2 red bands, that A and C are both transitioning down 1 energy level, so I should see the same amount of energy released, and so that would maybe show up then as the 2 red bands, red being low energy. Well then B is a transition downward of 2 energy levels, so that would release a little bit more energy, so I'm looking for something a little bit more energetic than red, so yeah, maybe like orange or yellow. And then D is the transition down 3 energy levels. So that then should be a release of a little bit higher energy. So maybe like the blue. If I had something like spectrum B, then there should be 2 transitions that are pretty large. Like I'm maybe 3 or 4 or 5 energy levels to get 2 bands in the violet part of the spectrum. And if it were C, then really each transition should be different. Like maybe one's just going 1 energy level, 2 energy levels, 3 energy levels, 4 energy levels, or something like that. But we've got 2 of them that are making the same transition, down 1 level. I kind of like that question, where you had to understand the Bohr model and then also how that relates to the quantity, the amount of energy released, and the colors of light then that we would see. That's a good one. And then finally, these seem to go pretty well, but there's some extra examples if you need them. If you are interpreting an orbital diagram and trying to decide the identity of the element, just add up the number of arrows. The arrows represent electrons, so in each of these, all you had to do is count the electrons, and that's all you have to say when you're explaining your answer. This element is aluminum because it has 13 electrons. Done. Easy. Here are a couple orbital diagrams that are not accurate. And so 2 of the more common errors, like the first 2 going up and down, the 2s orbital is not completely filled before they went up to the 2p orbitals. And we're supposed to always fill low energy to high energy. So technically I'm not supposed to move up to higher energy orbitals like p's until all lower energy orbitals are filled. Now they do say that these are supposed to be elements in the ground state. Well, if you did have something like this, I would have to say that the atoms are excited. And it does happen sometimes where, if we add energy, the electron can jump from a lower level to a higher energy level, but then that would not be a ground state configuration anymore. And it does tell me that all of these are in the ground state. So that's kind of the hint then that we should have filled the 2s before going up to the p's. Now, make note of something like this, where you've got 1 electron in each of the 2p orbitals, and that's great. When you get to p orbitals, like I guess the second two going up and down like on top of each other. The second two each have a problem with the p orbitals in that you're supposed to distribute the electrons one at a time amongst equal energy orbitals, and the key is that it minimizes repulsion. Electrons are all negative and likes would repel, so if I have equal energy orbitals, we'd like to evenly distribute those electrons to minimize repulsion. So if I had two electrons in p orbitals, they should each be in their own. Or same thing here, if I had the 2px, 2py, 2pz, each of the p orbitals should have their own electron if we've got 3 electrons to distribute amongst the p orbitals. It does not matter the direction of the arrow, though, if the electrons are in their own orbital. So like this here, this is okay. That one electron is going down and the other two are going up. It's arbitrary if the electrons are in their own orbital. Then who cares what direction they're spinning? It's just that if they were paired together, then they must spin opposite. And that too helps to minimize a little bit of the repulsion of having 2 negative electrons really close to each other. So that's okay in the first diagram to have 1 down and 2 up as long as they're in their own orbital. But these are maybe the 2 biggest errors that we have to look at with electron orbital diagrams. That you've got to go low energy to high unless it's excited, which these were not. And you've got to evenly distribute your electrons amongst equal energy orbitals, like P's and D's. Cool. Electron configurations. If you want to identify the element, 2 options. Option 1 would be to add up the electrons. So all the superscripts are the electrons. Just add up those superscripts. And then you could say, well, there's 14 electrons at silicon. Or you can look at the last orbital. So I could look at this 3p5, then go to your periodic table, find the 3p section, and count across 5. Oh yeah, it's chlorine. And then you just write a sentence explaining. Yeah, I added up the electrons, I got 15. 15 is phosphorus. Or it could be, I looked at the last orbital, the 3p1. The 3p1, that should be aluminum. That'll help identify the element. These all asked what was wrong with a configuration that was intended to represent iodine. So I might want to find iodine on my periodic table. Here it is. There's iodine. Okay, so then, get off of that guy. Iodine. Number 1, if I want to use the shortcut configuration, which I probably do because it's element 53, then you have to use the previous noble gas. So I really should go back to krypton. And then I write whatever comes after krypton. So I would be starting with the 5s for 2. And then remember how we marked it in? That when you get to the D's, they fill 1 less than what you might expect. The D's start in the 3rd energy level. So the first row of the D block is really the 3D. So then when you get to the 2nd row of the D block, this would be the 4D. And then we said the P's start in the 2nd. So 2nd, 3rd, 4th, which means then I would be back to the 5. 5p going across 5 for iodine. So first off, it should be krypton. Here's another thing that would be wrong in the second choice. It should end 5p5, not 4p5. And the D's would fill 1 less than you would expect. So it should be 4d10. Now, I want to mention something about this particular periodic table at the back of your book. So here's how I usually write my configurations. I write them according to the order that the orbitals are filled. I write them according to the order as indicated by the periodic table. Well, I would have written krypton. Then the next orbital filled would be the 5s for 2. The next orbital filled would be the 4d for 10. And then we would end with the 5p5. That's how I usually write them. That gives the proper filling order. Now, they have them reported a little bit differently on this periodic table. For example, now it's kind of small. They have it written as krypton 4d10, and then they go 5s2, 5p5. They're both okay. So some people had said that what was wrong is that it's supposed to have the 4d at the beginning or something. Yeah, the 4d is supposed to come before the 5s. No, there's something else that's like legit wrong with each of these configurations that are shown. Either of these are fine. This is fine. This shows the proper filling order. Which is how I do it, and it's fine. That's how the periodic table tells me to fill the orbitals. Lowest energy to highest energy. That 5s really has less energy than the 4d orbitals. Even though the 5s is a little bigger orbital, it's a low energy orbital. This is fine. This shows valence electrons grouped together. Valence electrons together. Valence electrons are all the electrons in the highest energy level. And so that's kind of what they're trying to show with the configurations on the periodic table given to us. That valence electrons are the highest energy level. So the highest level occupied by electrons is 5. And so they grouped them together. But you can still get that here too. It's any electron that's in the 5th energy level. These are both fine. And so either way you write them, it's fine. But it's got to be krypton, not xenon. It's got to be 5p, and it's got to be 4d. Oh. And then the last couple. Valence electrons then are all the electrons in the highest energy level, not just the outermost orbital. So all of these are examples that have electrons occupying the 2nd energy level. So I want to add any electrons that are in 2nd energy level orbitals. So I would include the 2s and the 2p. Cool. I like that. And speaking of valence electrons then, elements in a same group going up and down have the same number of valence electrons. So anybody in the first group, hydrogen, lithium, sodium, potassium, they'll all have 1 valence electron. Their configurations will all end something S1. 1s1, 2s1, 3s1. Everybody in the boron family has 3 valence electrons. Their configurations will all end something S2, something P1. Everybody has 3 valence electrons. It's just that the outer level increases as I go from boron to aluminum to gallium. Everyone in the fluorine family, or the halogens, will have 7 valence electrons. They'll all end S2P5. And everyone in the oxygen family has 6. S2P4. So you could have said any 2 elements in that group going up and down of the periodic table. And finally, element 118, oganesson, is the last known element to really be studied, although it disintegrates and decays in like fractions of a second. So nobody's ever made enough oganesson that we can really study it or use it for anything. Maybe someday. The key is figuring out like a good number of neutrons to overcome all the repulsion of 118 positive protons. Maybe at some point it's not even possible. So here's element 118 oganesson. They're asking about element 119. Someday 119 will probably be discovered, and when it is, how exciting. 119 will start the 8th row of the periodic table. No way. We want to write the electron configuration for element 119 using the noble gas notation. So you can take a huge shortcut here by just going back to oganesson, that would be a noble gas, and then you only have to write what would come after that. So it would really just end 8s1. Someday, I think we'll see it. It should be underneath francium then. Okay, so if you see anything in here where you're like, oh my gosh, I'm really stumped on whatever it might be, then let me know so that we can go through some extra practice.